Moore's law. There is nothing more sacred in all of computing than Moore's law. And as we'll see, it wasn't a law so much. There was no theoretical foundation behind it. It was an observation. But that's become really important in things like multi-core programming. All right. So in the 1950s and 60s, this was the architecture for computer systems, and this is called the von Neumann architecture, named after the computer architect John von Neumann. And there was an arithmetic logic unit. That's what does the add, subtract, multiply, divide. There's an accumulator. The accumulator is where certain values were stored that it was going to multiply together or add together. The control unit was for branching, like if statements, for instance, or loops. And then, of course, memory. And memory had two purposes. It kept data values and it kept the program, the machine code for the program. Also, there was a system clock. Nowadays, there's registers, lots of them instead of one or two accumulators, and a stack pointer. We'll talk about all of these. Okay, but here was Moore's observation, and it became known as Moore's law, that Gordon Moore was one of the founders of Intel. And, Intel in the 1970s started making CPU chips. And what he noticed is that every 2 years, or every year and a half, depending on whose story you listen to, every so often, the technology for making chips improved, and you could pack twice as many transistors on a CPU. Okay. And so, yeah, we kind of marched up. The red line is mine, is I found this. By the way, this is from Intel. Intel does great diagrams. NVIDIA does great diagrams. So when you see those diagrams, it's not that I'm promoting certain companies over others. It's just I'm swiping good diagrams wherever I can find them. But anyway, so I fit a red line through here. And if you look at the slope, and by the way, this is a log plot, but if you look at the slope, I get every 1.6 years, which is pretty close. Anyway, that's what this means, is every year and a half, the technology for making chips improved, and you could pile on twice as many transistors, which means you could go from an 8-bit machine to a 16-bit machine to a 32-bit machine. You could add more processing. You could add more register storage. You could add more cache. There's just a whole host of things that people could do. Okay, so this is what Moore said. What Moore's law was transistor density. Now, what does that mean exactly? Well, this is, again, Intel pictures, but this shows them taking a silicon wafer, this round thing, and they've etched multiple CPU chips on it, or multiple chips, and they'll cut these all off and mount them in little packages. Okay, but that's what increasing transistor density gave you, is you can pile more functionality in one of these little squares. And I found this diagram. I thought this was interesting. This is fabrication size, and it's a measure of how much can you squeeze down, you know, what it takes to make a transistor. And so the fabrication size in the mid 90s was 350 nanometers. Okay. And then, that seems small, but it's not in today's term. And then it dropped. And then again, Moore's law in action, transistor density. How close together can you put these things? And so down here in 2022, it was down to, well, about 7. And then I enlarged this piece over here, where now we are down into the 3, 4, 5, 2 nanometer processes. And it's harder and harder to get that to work. But that's where we are. And so the chip makers continue to drive Moore's law. Yeah, at some point there's going to be a limit, but right now they keep piling on more and more transistors with every new generation of chips. Okay, but a lot of people said Moore's law was clock speed. Clock speed doubles every year and a half. And that's not what Moore said. But the problem is it was true for a while because every time you made the transistors closer together, you could make the clock faster because the electrons had less distance they had to travel. Okay? So if you look at this graph, yeah, here's transistor count. And this again is a log plot. So it's, yep, transistor count is going up and up and up and up and up. But look at this. Clock speed, dark blue curve, is going up and up and up and up and up and up and up, and then flattened out. Moore's law kept happening. Moore's law of clock speed, which isn't really Moore's law, stopped happening. Okay? And here's the reason. Power consumed. And this is really important. Yeah, we can look at some other diagrams of this, but again, clock speed, megahertz, gigahertz, leveled out. Okay, why is this? It's because in order to power a chip, the amount of power you have to put in is proportional to clock speed squared. Okay. And if you pile that much power in to make the chip work at that clock speed, you also need to pull that heat out of there. That is, you're also piling in heat. So while it's enabling the clock speed, it's also heating up the chip. Okay. Um, yeah, they say that the limit is about 150 watts per square centimeter is how much heat you can pull off a chip before you can't pull off of it anymore. Intel made this, what I think is a very cute graph, is if we had kept increasing the clock speed like we were, well, this is a hot plate. That's how much heat would be coming off the chip. And that actually happened. You know, every so often you'd burn yourself up if you touch the chip by mistake. But if we kept going, then it would be like the heat of a nuclear reactor, the heat of a rocket nozzle, the heat of the sun's surface. Yeah, okay. Herein lies the problem. Now, you may have heard that Intel holds the record for clock speed at 9 gigahertz. Most of the CPUs you and I would own are 3 to 4 gigahertz. Somehow Intel cranked it up to 9 gigahertz. Now, again, clock speed squared, power and heat to be dissipated is proportional to clock speed squared. So you double the clock speed, you're going to get 4 times the problem. Well, okay, what did they do? This is what they did. They were cooling it. They were pouring, while they were cranking up the clock speed, they were pouring liquid helium onto the chip. Now, this presents some interesting possibilities. You could overclock your games and just have one of your friends sitting there pouring liquid helium on it. Now, why didn't they use liquid nitrogen for this? Liquid nitrogen is actually not cold enough. They needed liquid helium to make this happen. Like, wow. Okay. Interesting fun fact, nothing useful for us about that. And of course, there are more sensible heating solutions, and vendors are doing more and more all the time. With fans, you can, well, they increase the fan speed, increase these heat sink plates, put more of them in back to back. Cooling continues to be a big deal. And like the top end GPU chips are now talking about doing liquid cooling to keep that going. So it continues to be a big deal. You can keep an eye on this. Okay, this was an interesting fun fact. This has nothing to do with our Moore's Law discussion, but interestingly enough, as the fab size was coming down, the chips were getting cheaper to produce right up until 28 nanometers. And I don't know if there's some physics there, but at 28 nanometers, it kind of leveled out. So the cost to make a chip is pretty constant now, but it was dropping for a while. Okay, multicore. Moore's law of transistor density is still going on, which means we can pile more and more and more and more transistors on a chip. But we can't increase the clock speed. So how are we going to get more performance every year? We're going to take advantage of those more transistor capacity and turn those into auxiliary CPUs. So yeah, you got a CPU and we got some more CPUs. And if you can figure out how to use them together, then you'll get more performance. Okay, this is called multi-core. Multi-core means we're packing more CPUs onto a single CPU chip. This also let us do things like single instruction, multiple data, floating point units. We'll get to that later. But every time they could put more transistors on a chip, this set the architects free. Like, oh gosh, now we can do other stuff. Okay, so if you have more than one core, but you're not doing multi-threaded programming, that's still a good thing. Okay, when you're even if you're not doing multi-threading on your system, you're probably running a web browser and Excel and Word and watching a movie at the same time. So having multi-core lets multiple programs run together smoothly, even though none of them is doing multi-core programming. Okay. And even if we only have one core, multi-threading is still a good thing because we can do multiple things and they will time share. And so multiple parts of your program can be running together and they're time sharing the single CPU. But what is cool is when you have both. Okay. When you have multi-core, so you have more hardware processors and multi-threading, more paths through the code, and each one gets its own core. That's the sweet spot right here. And that's really what we're going to talk about when we talk about using OpenMP. Okay, and that's known as multi-threaded shared memory multi-core architectures. So this is going to be a great thing. Okay, so there's interesting stuff in architectures. Like for instance, this was the one core architecture. The green is the state. Okay, that's like what program counter, where's your stack pointer. The red is the core and the blue is the cache memory. So one core, one state was like this. Then when they went to two cores, yeah, they doubled everything. And when they went to four, they doubled everything. So like this. But Intel played other games where instead of jumping from one complete set of things to two complete set of things, they made a stop in the middle where you had one core, but two sets of states. And this let you swap between two threads really easily because the chip knew for the other thread what its program counter was, what its stack pointer was. And this is called hyperthreading. And we'll talk about this more in a different note set. So this was one of everything. This is two of everything. This is four of everything. But Intel created these stops in between where you had the same number of cores, but double the states. Okay, so here is one core, two states. Here is two cores, four states. Again, this is called hyperthreading, and we'll talk about that in a future note set. And I got this from a PhD thesis. It was somebody who actually had been in this class and then used it in his PhD research. Unfortunately, he did his y-axis upside down. So he's doing elapsed time. So better performance is down in this case, but you can see what he got. When he ran one thread, he got this. He basically doubled his performance when he got two threads, doubled it again when he got four, and almost doubled it again when he got eight. And so these are the kinds of results that you can see when you do multi-core programming. So there we are. Moore's law lets us pack more transistors on a chip, and what that lets us do is add cores, and that lets us achieve better performance, even without increasing the clock speed.